Okay, hi everyone. This is my video number 33. In this video, I'll talk on why is blur? Why is not clear? All right. Okay, so I'll talk on Stoke theorem. I'll talk on Stoke theorem. Stoke theorem. So the Stoke theorem, we have a definition of the Stoke theorem, says that the integral over C, closed integral over the curve C, where C is closed curve, f dot dr. This can be written as, or you can write as, integrate over the surface del cross f dot n ds, where f is a vector field PQR with component PQR, and its partial derivative are continuous, and S is a smooth surface, and C is smooth curve. C is smooth curve. Okay. Now, the Stoke theorem says that, or this relation says that, the closed integral of a closed curve can be written as a integral over the surface. Okay, what does that mean? So if you have let's say we have this is our surface, this surface S. Okay, this is our C. Okay, those C is full circle. It's close. It's a closed curve, not necessarily circle, but it's closed curve. And N is a normal to the surface. N is a unit normal to the surface. Okay, so this theorem says that instead of integrate over the closed curve here, where this closed curve is obtained by, if you look at from z positive, basically it's projected on that plane, so we have a closed curve there. We can integrate over the surface, and this process will make us, or we make our job much easier. Okay, I'll give you example of doing this. Example. Let's say we want to determine double integral over that dot n ds, where S is a surface given by x plus y plus z equal to 2 in the first octant, and F is given as xz, like that, xz, yz, and xy. Okay, now if you look at this surface, you can sketch this to sketch surface. Okay, let's just sketch the surface. So XYZ. So look at this surface. On X axis, YZ is 0, so X equal to 2, so we have 2. On Y axis, XZ is 0, Y equal to 2. And Z axis, XY is 0, so Z equal to 2. On XY plane, Z is 0, so we have X plus Y equal to 2, which is a straight line crossing at 2, 2. Right, so we have a straight line. That, and we have on XZ plane is Y0, so we have X plus Z equal to 2. So we have that, and on YZ plane X is 0, so Y plus Z equal to 2. So we have that. Okay, so this is our surface S. So if you want to integrate, so because the Stokes theorem says this integral is equal to C f dot dr. Okay, if you use this integral, we need to consider that surface. We need to consider that curve. So which means we have C1, C2, C3, and we need to evaluate them one by one. Now instead of doing that, we can use the double integral over the surface. How to do that? We need to find out what is del cross F and so on and so forth. Okay, so let's do this. So for del cross F, you can write this as a ijk. Del is del x, del y, del z. Okay, and f given as xz, yz, xy. Okay, so you can find out this. This is so for I, so we have del y, so you got x, right? So we got x minus del z minus y. Del for ij component del z, so we got x minus del xy. Is that correct? X minus y, correct. For z, for key component, we have the z that's 0, that is 0, so you got 0 there. Okay, now we need to determine the n. How to determine this n? Now look at this. If S is the surface given by f xy, okay, I can write this as a z minus f xy, that equal to 0. Okay, on the left hand side here, I can say, let's say this is let's give a name. Let's call this function g, where g in this case is a function of x, y, z. Okay, now this surface S can be written as that function. Okay, now if you consider this function as a surface, in order to find normal to the surface, what we need to do is we apply the del operator to it. So we have del g. So this del g will give you normal to the surface. But remember that you need normal. Not just normal, but you need normal. Okay, fine. Now, so in order to have del g here, so you just need to differentiate this. So we have this. Differentiate that, you got negative of f of x, negative of y. This is differentiation with respect to x, with respect to y, partial derivative. And differentiate with respect to z, you got 1. Okay, now we need n, so I need space, some space, I put it here. Our n is given as del g over magnitude of del g. This is unit vector. Now what is ds? Your ds, because this is a surface, you need to write in term, because you got everything on x and y, you need to write on xy, and here given as del g. If you put them together, n ds, that will give you g over g dx dy. Okay, you can cancel out that, so what left is just del g dx dy. So in this process, okay, in order to evaluate this integral using the Stokes theorem, or this integral over the surface, so we need to find those n, normal, unit normal. So our n, you can just find the del g. So which means that this del g will give you normal to the surface. Okay, now, so we need to find those things. Where is our f? This is our s. S is given as we have x plus y plus z equal to 2. I can write this z equal to 2 minus x minus y. This is our fxy. Okay, so differentiate that with respect to x, because we need fx, we need fy. Okay, we need fx, we need fy. So we differentiate respect to x, fx. So we have this minus 1. We differentiate respect to y. We got minus 1. Okay, so therefore our n is, you can write as, we have minus fx minus fy, don't forget that minus, and 1 because we write function in terms of z, so we differentiate z, that's we got 1, so that's why we have 1 there. Okay, so now this gives you negative fx is 1, so you got 1, we got 1, we got 1. Okay, so therefore del cross f dot n, you can write this del cross f is, we already obtained, we have x minus y, and 0 dot our n is 1, 1, 1. Okay, so solve that. So we got x minus y plus x minus y plus 0, that give you 2x minus 2y. Okay, so now you can evaluate this. Okay, so if you put in those integral, we integrate over s, those given as that, so we have 2x minus 2y dx dy. So what is dx dy, and what is the limit? How about the limit? So the limit is over the surface. You have to remember, look at this thing. So our x is y from 0 to 2, or you can have y from 0 to that line. So this line is given as what? This line is given as, this is on xy plane. So on xy plane, z is 0, so which means x plus y equal to 2, that we have y equal to 2 minus x. Okay, and x from 0 to 2. So I can transfer this thing. I can write y from 0 to 2 minus x, alright, and x from 0 to 2, then 2x minus 2y dy dx. Okay, so I think you have no problem to evaluate this. You can do this. Alright, so if you proceed that, so what we have, those two you can factor out. I can have x from 0 to 2. You integrate respect to y, so we have xy minus y squared over 2 over, so y from 0 to 2 minus x dx. That. So that gives you to integrate x from 0 to 2. So y is 2 minus x, so x 2 minus x minus 2 minus x squared over 2 and minus 0, right? So dx. So simplify that. So we have 2x from 0 to 2. This is 2x minus x squared, yeah, minus that one is half. We have 4 minus 2x plus x squared dx. Okay, so what we have, this equal to 2 x from 0 to 2 x squared minus x squared. This is minus half, so minus 3 over 2 x squared. Then we have for x 2x here plus x, so plus 3x. Okay, and then here you have minus half, minus 2 dx. So that you have 2, that you get negative 3 over 2 x cubed over 3 plus 3 over 2 x squared minus 2x from 0 to 2. That cancel out. Now I think you can find out the result. Okay, just do it yourself, that part. Now if we integrate using line integral, I think you can do this one, line integral over c f dot dr. So in this case, what is our c? Look at this thing. Look at our figure here. What is our c? Our c is here. This is our c. Okay, so you need to consider this as a c1, you need to consider that as c2, and you need to consider that as c3. Okay, and you need to find what r is. It's not difficult. You can do that. What r is, then you can find this. Okay. All right. So that's the first example. Now I would like to give another example. You can solve those things. Yeah. Let me give you another example. Let's say I have okay, using the Stoke theorem, example, using Stoke theorem, evaluate those s f dot n ds. Okay, f is given as minus 3y 3x z 4. Okay, s, okay, s is a top portion top portion of z1 over z2 and a ellipsoid 2x squared plus 2y squared plus z squared equal to 1. Okay, so we're going to solve this. First things, I would like to sketch what is our surface. This is our surface S. Okay, so if we sketch this, so what we have, it's not compulsory that we have a lot. Look at that. On x axis, you got y0, x0, so you got x is 1 over z2. So we have here, this is 1 over z2. Positive, negative. Same for y. Positive, negative. But z is 1. Z a little bit bigger. So we have it look like that. So let's say this thing here. Okay, and we have this. So that's our ellipse. Okay, that's the ellipsoid. And cut by z 1 over z2 somewhere here. This is z equal 1 over z2. Okay, and at the z equal to half, where that line cut the ellipsoid, so we have a circle here. Okay, so this circle is of radius 1 over z2. Yeah. Okay, so you can have this circle. This circle is given by this circle. This is z equal to z2. You can substitute there. So what you have, 2x squared plus 2y squared plus 1 over z2 squared plus equal to 1. Alright, so we have 2x squared plus 2y squared is equal to, this is 1 over 2, so we have 1 over 2. Alright, so x squared plus y squared is 1 over 4, which is a circle of radius half. Circle of radius half. So which means here is half. Here is half on x half. So if you transfer this into xy plane, so we have just that. This is half. This is half. A circle of radius half. And on z we have, of course, we have a surface here. Okay, we have surface here. That surface, that part here. Now, so we have the surface. Now what is our s? Our s is, we have 2x squared plus 2y squared plus z squared equal to 1. I can write this in terms of function of x and y. So I can write this as z squared, or z is equal to square root of 1 minus 2x squared plus minus 2y squared. This is our fxy. Okay, now what do we need? We need to find this, and we need to find n. Remember that what n is? I have shown earlier. N is negative fx, negative fy, and 1. Okay, we need to find fx, we need to find fy. What is fx? Fx is given by the surface, but you write in terms of z. Okay, so let's find fx. What is fx? Fx is, means we differentiate that with respect to x. So what we have half 1 minus 2x squared minus 2y squared minus half. Differentiate inside, so we have minus 4x. That cancel that, we have 2, so that gives us negative 2x over that 1 minus 2x squared minus 2y squared. Look complicated, but it's not difficult. Fy, you can differentiate that respect to y. You got minus 2y over 1 minus 2x squared minus 2y squared. So therefore, our n is given as minus fx. This is our fx minus, and we have minus a positive, so we got 2x over square root of 1 minus 2x squared minus 2y squared minus fy. So we have minus fy is given here, so we have 2y over 1 minus 2x squared minus 2y squared, and we have 1, so we have 1 there. So that's our n. Now you need to find this curl f. Okay, curl f, that, so we have I j k del del x del del y del del z and it's not good. Just a minute. It's okay. I feel got it. So where is our f? Our f is minus 3x minus 3y minus 3y 3x and z4. Okay, then we do this. So what we have, del x, so that's 0, so for y we got that 0, so you got 0. For k, so you got this is minus 3, so minus 6, right? Minus 6. This is positive, sorry, this is negative. Okay, so del cross f dot n, that give you 0, 0, minus 6. Is it minus 6? No, 6, positive 6. Dot, those n is given here. So we have n is 2x over those 1 minus 2x squared minus 2y squared, 2y, 1 minus 2x squared minus 2y squared, and 1. Okay, solve this. You got 0, 0. So you got 0, 0, 0. So you got 6. Now our integration is integrate over s. So we have that give us 6 ds. So this is, we integrate, this is dx dy. This is a circle. Okay, so r is half, so I can change that r from 0 to half. This is a full circle, so theta is from 0 to 2 pi. Okay, we have 6 dx dy. This is r dr d theta. I think you know this thing. We do this substitution, x equal to r cos theta, y r sin theta, dx dy. So we have r dr d theta. You substitute everything into this, then we got this thing. Okay, if you solve this, so what we have 2 pi there, 2 pi, we have 6 there, we have r squared over 2, r from 0 to half. Cancel out, so we have 6 pi. That one is 1 over 4, that gives you 3 over 2 pi. Okay, if you do this, f dot dr is not easy. I tell you, it's not easy because it's involved x, a circle, that circle. Then you have to write as a x squared plus y squared equal to 1 over 4, and you have to write y in terms of x, positive and negative. 1 over 4 minus x squared, that's for your c. Okay, that's for your c, that's c. And then you need to substitute x equal to t, then y in terms of t, 1 over 4 minus t squared. Then you need to find d, here dx, this is dt. You need to find dy, what is dt. Okay, substitute everything there, because here what we have, f dot dr is basically what we have, p dx plus q dy plus pqr r dz. Then you need to integrate that over c, integrate that over c, you need to integrate that over c. Okay, where your c is given as that. Okay, so you have dx dt, your p is your f minus 3y, your y is here. You need to substitute everything there. Then integration that involves square roots, and you have square inside there, is not easy. You need to use a trigonometric substitution, the inverse trigonometry, I think. So it's not easy. But by using the integration over the surface, so the process is much more easier. Okay, so I have some exercise for you. So let me give you some exercise. Let me give you some exercise. Verify Stoke theorem for f. For f is given as z squared minus 2x and y cubed, and s is the top portion of sphere, of a sphere, x squared plus y squared plus z squared equal to 1, cut by z equal to 0. Okay, you get answer. You should get 2 pi minus 2 pi. I leave it you to do that. And what else? I have another exercise. Just mix exercise for you to do. Okay, mix exercise. This is not the Stoke theorem. F, this is number 1, this is number 2. Given s, f is 2x plus y cubed, 3xy squared plus 4, this is squared, plus 4. Find f, this is potential function, you know, so means this is the conservative vector field. You can show that. You can. This is conservative vector field. Show. You show that. Okay. Find the potential function f such that del f equal to f, and hence evaluate from 0, 1 to 2 to 3 f dot dr. So you know that if our function, our vector field is conservative, then the integration is independent of the path connecting 2 points. All right. Number 3, evaluate C f 5xy dx plus x cube dy, where C y equal to x squared, y equal to 2x. Maybe you can use a green theorem. I'll leave it to you to test that. All right, I think that's all for this video. Thank you.